Okay, so let's do an example. Solve x double prime plus x equals 1. Okay. Now, this problem is non-homogeneous because it has that 1 over there. So we're going to split it into two problems. We're going to analyze both this problem and the homogeneous problem. It's x of h double prime plus x of h equals 0. And x of p double prime plus x p equals 1. So this one's probably easiest to do first, just because it's a pretty simple function on the right-hand side. We're going to look at what kind of function will take a second derivative of it plus itself to give us a 1. Now, again, we saw an example of this before. Let's start with a constant, okay? So a constant second derivative is 0 because its first derivative is 0. And then we say, okay, what constant gives us 1? Well, that's just 1. So xp equals 1. Woohoo! Okay, so we got that part. That one was pretty nice and easy. Now let's look at the homogeneous piece. And to do that, I'm going to not solve it, because we haven't developed any methods yet. I'm going to rewrite it and guess. I'm going to guess a function. What kind of function do I know whose second derivative equals the negative of itself? Okay, so before this looks pretty similar to what we had with the exponentials, right? If you take e to the t say e to the negative t. If you give e to the negative t, we take a derivative, we get negative e to the negative t. But now we need a second derivative, and that spits out another negative, which makes it positive e to the negative t. So it doesn't work out with exponentials. But there is a function. What about cosine? If I take the derivative of cosine, it goes to a negative sign. And if I take the derivative of a negative sign, I get a negative cosine. There we go. So on this side, I have x1 equal to cosine of t. I know that's a solution. And since I went cosine, sine, cosine, what if I start with sine? Take a derivative of sine, I get positive cosine. If I take a derivative of cosine, I get negative sine. That one works too. So now I have two functions, both of which satisfy my homogeneous equation. I just rewrote it to inspect it a little bit easier. Now I want to check to see if these are linearly independent at all points, or if there are some points where they are dependent. So let's check the runs. We know we have enough vectors. We just don't know if we have the right kind of vectors, right? Because we're looking for a second order solution space, two-dimensional solution space. There are two solutions. If they're the right kind, we have them all. So Wronskian of x1, x2 equals. First we put cosine of t, and then we put sine of t. And then we take their derivatives. Minus sine of t, and then positive cosine of t. Okay, so we take the determinant. This is a nice 2 by 2. Multiplied down, we get cosine squared of t minus, multiply back up. That negates the negative here, giving us a plus sine squared of t. And we want to check to see if this is not equal to 0 for all t. So let's see if we can simplify it a little bit first. Oh, there it is. Cosine squared plus sine squared is 1. And that 1 is never 0. Which means that our functions, sine and cosine, they're linearly independent for all values of t. For all time, in a sense. Which means that as long as there's no discontinuities in our differential equation, let's check that. Nope, 1, 1. Nope, no discontinuities there. That means that our solution space can actually be negative infinity to positive infinity. So we can have the biggest solution space possible, all real numbers. Okay, so what does that mean? Well, since the Wronskian is never 0, and we have enough functions to match the dimension of our space, we know that the homogeneous solution is equal to the span of x1 and x2, which, well, I'll just write them in there. The span of cosine of t and sine of t, which I can also write as c1 cosine of t plus c2 sine of t. Notice these constants, which are actually the constants of integration we would get by integrating this, show up without any integration. There is actually some integration involved. We're just jumping through a very sneaky shortcut. Not sneaky. A very helpful way around that integration, using the patterns in the linear patterns that exist here. So let's back it up. We know a form of XP. We know one solution that solves it. We also know all possible solutions that make the left-hand side equal to 0. That means that the general solution I keep thinking in terms of vectors. X of t equals x of h, x p plus xh. This full solution is equal to r1 plus c1 cosine of t plus c2 sine of t, like that. And sometimes we'll write it with the xp on the other side, like x of h plus xp. The reason we would do that is sometimes we'll want to have that constant as far away from the constants as possible, the 1, and then we can just subtract it off the other side. But that is our general solution. This describes all possible solutions to the differential equation x double prime plus x equals 1. Now again, as we go through chapter 3, we'll develop actual methods for going through and finding the particular solution and finding these homogeneous solutions instead of just looking at it and guessing. But sometimes the patterns are there and they can be obvious. So keep your eyes out and look for those. That's one of the key things about differential equations is it's looking at how functions and their derivatives relate to one another, finding the patterns, using the patterns to skip past as much integration as possible, to skip past the underlying mechanics of the solution to write it down in a succinct form.